All right, ladies and gentlemen, we want to start with the concluding part of heteroscedasticity. Remember, we said that heteroscedasticity occurs when the error term given the independent variable is not constant. Okay, it's not constant across observations. Across observations. Now, it's a big problem when it is even in panel data, which we shall learn. In panel data, you don't just have observations, but you have observations and over time. So when it is not constant across individuals and across time, that is serious. And we'll look at that, okay? But here, how do you deal with heteroscedasticity? Because when it is happening, watch what the reason. The reason is because there is a possible misspecification. You did not specify the data, the functional form well. That is one reason. Another reason is possibly omitted variable bias. And so we have already looked at how to transform the data using logarithms. We have looked at the white heteroscedastic robust standard error. And we saw the last time that one, when you use that one, it was able to correct. It still maintained the estimates, if you can remember. The estimates were still maintained, but the standard errors were so much corrected that it led to very significant p-values. Fantastic. That was a wonderful result that we had. The final one, which is more or less like a blend of the two, is the use of the weighted GLS, WLS, or feasible GLS, okay, which is actually the application of the weighted least squares. So we're going to understand each other then. I'll be going slowly. If you have any challenge at any point, kindly let me know. All right. So these commands that you are seeing here were commands that we use to correct for the standard errors. Okay. And I also mentioned a particular kind of way of solving not just heteroscedasticity, but even autocorrelation. You remember I said that. I mentioned it as a robust West estimator. And we indicated that that was the best so far. So let's start. Weighted least squares, or GLS. If the heteroscedasticity form is known, and I'll explain later on what I mean by it's known, then the weighted least square can be used to estimate the model using a function in R called the GLS function, or a feasible GLS will be estimated. Now, if the heteroscedasticity is known, and when I say is known because you calculated it, you found it, but if it's known up to a multiplicative constant, okay, so if you look at this, okay, this is heteroscedasticity. There is the fact that you have an I means that it is heteroscedastic. The H here means that it is known up to a multiplicative constant. So in other words, the heteroscedasticity is known with certainty. If that is the case, then there is something you can do. We can transform the regression model, estimate the transformed model by OLS. But you see, now you are estimating the transformed model by OLS, so it gets a new name. And that is what we mean by GLS. So how do you transform the model? And I'm going to do mathematical transformation of the model. I'm going to go slow. You see, there's something that is not clearly meaning. First, you're going to multiply the errors by 1 over the square root of the constant variable that you mentioned. Now, please, this is a standard thing that has been developed. You can do 1 over the square root of that, or you can just do 1 over the H. And when you do that, it will make the residuals homoscedastic. So the residuals are going to be homoscedastic when you take this. Now, how do you do that? Practically, first of all, you would divide each of the residuals by the square root of that constant. And then the variance of that, you take that, which will mean this. Watch it, how it becomes homoscedastic. If you take the variance of this over that, okay, and then you fish out, remember, you can fish out. If you multiply through, okay, you can fish out the variance of that over, and then you can have 1 over hi. So when you have that 1 over hi multiplying the variance, which comes back to the point I said 1 over hi, which is on top here, you now get the variance of the u. And once you have the variance of the u will become constant. And you can see that the 1 over hi, when you square it and then you have its hi, the hi will cancel the hi. And then you have 1 multiplying the sigma square. And that will be equal to sigma square. And that sigma square means that the variance is constant. Remember, we said that the variance is not constant when there is no I. Now, you can see clearly that the variance is constant. So this is a mathematical way you can get the a constant variable to multiply through. And you can estimate this later now by OLS. Okay. So let me use how you can now estimate it by OLS. So you can estimate the transform model where all the variables and the constants are multiplied by that. Okay. So let's take the upper part of this model. The upper part of this model, if you look at the upper part, the upper part is the regression model. Look at the upper part. The upper part. Okay. In case you don't see, I need to probably go and use some ways to bring out the point. Okay. So when you look at this upper part here, okay, this upper part is the regression model. Now we divide each one by the square root of the hi, which is like multiplying it through by 1 over the square root of hi. When you do that, we can now have a new model, which is what you see here. Now this new model is having a star, which means that something has been done to the dependent variable and each of the independent variables. Okay. And that is what we mean by the transformed model. That now becomes the transformed model. Okay, let me just clear this. So that transform model can now be estimated by OLS, and then you can now deal with the situation. So it says that this model has a homoscedastic error, no longer heteroscedastic error, can be estimated by OLS. Okay? So you're now estimating the OLS on the transform model by multiplying the variables by 1 over the square root of it. And this is equal to estimating the original model. And I want to repeat that. This is equal to estimating the original model by GLS. So estimating the new model, okay, this new model, estimating this new model by OLS is like estimating the original model I showed you up here by GLS or weighted least square. GLS is generalized least square. And the weight, because when you hear the word weighted, it means that there's a weight. The weight is 1 over h. Now, in weighted least squares, observations with higher variances have less weight. Okay? And those with lower variances will have high weight. And there's a bit of complex mathematics of deriving this. So the OLS gives each observation equal weight. Now, the original OLS estimator that we know, if you guys can remember this, through the variance covariance matrix, this was the original OLS estimator. Watch it. This is it. Now it's going to change to a GLS1 okay, because of the weight that we gave to it. So the new GLS estimator now is this here. This is it. Okay. If you look at it, there's an omega that has been added there. Omega. Everything else is almost the same, but the only thing is that there's an omega raised to the power -1. Okay. That omega raised to the power -1 is just a transpose of the summation sign. Okay. The summation sign that will be incorporated during the, what do you call it? During the multiplication of the model. Okay. And that will capture those multiplication summation signs. And so finally, you will notice that beta OLS, which wasn't anymore, it wasn't blue, okay? It wasn't anymore best linear unbiased estimator, okay? Now that we've estimated with the GLS now will have a variance covariance matrix different from the OLS as what you see here. And the GLS will become unbiased as well as consistent. So in short, if you want to ever correct heteroscedasticity, you can estimate the model, okay, the original model with a GLS. That's the point, with a GLS, which we will do. And once you do that, you're likely to correct the situation. Guys, you are going to see some incredible thing when you do that. Okay. So, but sometimes people get a little bit confused with what is the difference between GLS and OLS and, you know, certain things like that. Well, the difference has to do with assumptions. Okay. And assumptions about the error term, assumptions about the variance of the estimate. Okay. And sometimes one can choose the GLS over the OLS if the sample size is big enough. Okay, that is what we mean by if the n approaches infinity. And one can easily get the GLS estimate when there is heteroscedasticity than when you do by OLS. You will not get proper estimates. So in GLS, what we do is that we divide through by the standard deviation, similar to the WLS. Okay. Now, you might hear of WLS, you might hear of GLS. Okay. They are almost the same. I don't like to, and I'm going to show the two of them. They are almost the same. It's a way you choose that constant to multiply. So here is this. In the case of WLS, okay, you are multiplying by 1 over the standard deviation. Okay. In the case of the GLS, we also multiplied it by 1 over the square root of the HI. So they are more or less the same. They are more or less the same. So please note that. Okay, now what about the feasible GLS? And you might hear this in further studies, feasible GLS. I will talk about that pretty soon.